Okay, so we left off, I guess that would have been last Friday, huh? Okay, so we talked about Bayesian classification. And basically, we wanted to know what is the probability that... I forgot my notes. Oh, geez. Okay. Well, we said, what is... Did I say T is the label of the class? Okay. What is the probability that T belongs to some class given... I'm going off the kind of your X new and your matrix of X and vector T, right? So this is kind of your... I apologize if my my notation doesn't line up with your notes from Friday because I'm going off the top of my head. I mean, the concepts will be correct, but the notation might be a tiny bit different, right? So these are the observed X values, and this is basically the probability that this observation belongs to class C, belongs to class C1, okay? And let's say there are 3 different classes, then the probability of T equal to C1 given X and T plus the probability of T belonging to class 2 given X and T, and the probability of T belonging to class 3 given X and T, this would add up to 1, right? And we said, okay, something happened. Give me a second. And we said that this thing is going to be the likelihood, probability of X new, given that that we belong to class 1, and given our training data, times the prior that that T belongs to class 1 divided by the marginal. And this part, the likelihood term is a different probability well, the likelihood term is calculated using a different probability distribution for each class. Okay, so you have a probability distribution for class 1, you have a probability distribution for class 2, you have a probability distribution for class 3, and then you say, well, what is the likelihood of getting the values that I observed in X new from each of those probability distributions? Okay, and you combine that with the prior probability of that classification, and basically you calculate that across all possible classes, and the marginal is just going to be the sum of those numerator terms, so that when everything adds up, it adds up to 1. Okay? So I'll just do a very simple unidimensional example. Okay. All right, and we can say you can, maybe there's a stack of, I don't know, stack of shirts, okay? And the shirts are either going to be small, medium, or large. And, you know, as much as companies want their clothes to be identical, if you have two small shirts, they're not going to be the exact same size. And if we had a very accurate scale, their weights might be a tiny bit different, okay? So anyway, let's just say in the stack of the shirts, we have, I don't know, 30% small, 50% medium, and 20% large, all right? And then let's say based on, so we're gonna just do, so using our training data, we make MLE estimates of mu for each class, all right? And so we will say, I guess mu and sigma. And so we'll say the weight, if given T is class small, will come from a normal distribution. I don't know how much shirts are supposed to weigh. 240 grams with a standard deviation of 3 grams or something like that. Here, let's make this interesting. Let's say this is like a low quality manufacturer, so there's like a large, like, so high quality manufacturers, like there's low tolerances on everything, but let's just say this is a low quality manufacturer, so everything's like all over the place, right? And then we'll say the weights, if they're mediums, will come from a normal distribution with mean 250 and 15, and then with weights, if the classification is large, it's going to be normal with mean 260 and 15 or something like that. Okay, I guess maybe t-shirts is not the best. I should have done like tomatoes, because at the grocery store they'll have like, or apples, right? They'll have like small apples, medium apples, and large apples, and they're all supposed to be like sorted by size. But you know, sometimes you're like, this was classified as medium, but it's like a huge apple, you know. Like, okay, well, anyway, so you've got something that looks kind of like this, right? And because of the great overlap, if we observe an observation at, let's say, 253, all right? So let's say x is 253, and the question is, what is the class? Okay, so the prior distributions, so the prior on t equals s is going to be 0.3, and the prior for t equal to medium is 0.5, and the prior for t equal to L is 0.2. And here we're going to ask, okay, based on this value, 253, what is the class? Does that make sense? Okay, and so why do you even bother naming these things small, medium, large if they're all the same? But okay, so what we got to do is we got to say, okay, well, how likely are we to get 253 if we came from this distribution, right? How likely is 253 from this distribution? So that would be, right, so how likely is 253 to come from normal 240, 15, right? So we can answer this using dnorm. We can ask dnorm 253, 240, 15. Or we can use the normal distribution equation, and we should get the same answer. Google already knows exactly what I want to do. Okay, and we're gonna just copy. Come on, work with me, please. Can I copy this? No, it says too much. Come on, computer. You can do it. Okay, which should be equal to getting, you know, x is 253, and mu is 240, and sigma is 15, right? So if we plug this into here, we'll get the exact same thing. So this is the likelihood term. So this is the probability of 253 given t is equal to s, right? And we would multiply this by the prior probability of t equal to s. So I'm going to go ahead and I'm going to just cheat and use r to get this answer rather than plugging it in. But if you had to, you could do it, right? Oops. Did I do something wrong? Warning, do try catch. Why am I getting a... That's weird. D norm? Am I doing something wrong? Huh? That's weird, right? Okay. 0.018269. 0.018269 times 0.3 is the prior probability, and we get and we'll just call this A. Okay, 0.00548. Okay, and then we ask, same question, how likely is 253 from normal 250, comma 15? Okay. So I get 0.026. So the probability of 253 given class is medium times the probability that t is equal to medium. This is going to be 0. What did I say? 0.026. 0.26069. And then the prior probability of being class medium before we looked at any measurements was 50%, right? Because our stack of shirts were 50% medium. And so this value times 0.5 is 0.013. 0.013034. Okay, and I'll call this B. And then lastly, we'll do the same thing. Probability of getting 253 if our class is large. So, okay, and this turns out to be 0.00477, and we'll call that C. Was it 00477? Is this okay? So I'm just saying, what's the probability of getting this thing under this distribution multiplied by the prior probability? What's the probability of getting this thing under this distribution multiplied with the prior probability? Yes?
So you said the prior probabilities here we obtained from looking at the training data?
Yeah. we looked at the training data and we said in our training data, 30% of our shirts are small, 50% are medium, and 20% are large. We're hoping the training data is representative of the test data or the population, and so that's what we're using. If we had other information, like if we said, you know what, I'm an expert on t-shirt manufacturing, and I know that smalls are produced at a rate of 25% and mediums are produced at a rate of 40% or something, we can use that using that prior information. Yes?
Then, like, because before we've written like matrix X and then vector T, the responses. So you're saying we only looked at T?
Yeah, we basically just looked at the T's and said, how many smalls, mediums, and larges do we have, right? And then we used the vector X to come up, the combination of the X's and the T's to come up with the, basically our maximum likelihood estimates, which I said was 240 and 15 for class small. So basically I would just, using like dplyr, I would have done group by class, size, and then summarize, mean, and then not exactly standard deviation, but you know, like the MLE estimate for the variance or something like that. Is that okay? So so we do that, and okay, and then so these are each of our numerators. We have 3 numerators, and so my marginal is just going to be the sum of each of these 3 terms, 0.00548 and plus 0.013034 and 0.00477. Okay, so this is my marginal. This is what goes on the bottom. And so when we normalize this, so basically I'll just call this the marginal, which will be the sum of A, B, and C. Okay, so my marginal comes up to be this, and then I just do A divided by the marginal, B divided by the marginal, and C divided by the marginal. Okay, and what I'm getting is that after all the information, its probability of being a small is around 24%, probability of being medium is around 56%, and the probability of being large is around 20%. Okay? Maybe I'll just copy this. Okay. Well, I'll be sure to include my R history in your notes. All right. Is that okay? So this is how we would run a Bayes classifier for our for a unidimensional variable. The if we had multivariate data, which is almost all the time, not all the time, but which is more often than probably the unidimensional case, then we would have to estimate, do maximum likelihood estimation for a multivariate distribution. And sometimes that gets a little complicated because, I mean, the MLE estimates for the mean is just, you know, the mean of each thing, but then you have to estimate the covariance matrix, which, depending on how many data points you have in each class, the covariance matrix could be wildly off. Okay, so if you happen to have like only 4 or 5 data points in one of the classes, the covariance matrix itself has a high amount of variance from one random sample to another random sample. Okay, so let me just say this. For multivariate data, okay, the process is similar. okay? But requires us to estimate covariance matrix between the x variables. And if there are only a few observations, then our MLE covariance matrix will have a high amount of uncertainty. So instead, we have the naive Bayes classifier. Okay. So instead, okay. In the naive Bayes classifier, we are basically saying, okay, I know this model is not a good model, but perhaps it can outperform the correct model. Or not, maybe not even the correct model, just like the other model that might be better. All right, what is the naive Bayes classifier? Basically, we're going to say that the different x variables are independent of each other, okay? So the naive Bayes assumption, or the naive part, is that the x variables are assumed to be independent. Okay, so perhaps the true model is a multivariate Gaussian that looks like this, right? And you've got maybe your mu is 0,5, and then your covariance would be something like, I don't know, 150, and then there's some kind of covariance term here, 40 and 40 or something, right? There's covariance between the two sides, okay? Well, the naive Bayes, basically, we're going to say it's not even multivariate Gaussian, it's going to be just the product of two independent Gaussians. So instead of multivariate Gaussian, our joint distribution is the product of two independent Gaussians, right? And so what does that look like in the picture? Well, it looks like concentric ellipses where the, what do you call the axes of the ellipse? Whatever. There's some name, right? It's not the axis of an ellipse, but you know what I'm talking about, okay? Basically, the axis of the ellipse are perpendicular, okay? Rather than over here, you've got like, the axes of the ellipse are not parallel to the x and y axes. They might be at some kind of angle. And over here, we're going to say this. And then if we were to calculate a sigma matrix, which is unnecessary because this is just a product of Gaussians, but if we were, we would have zeros here and here. Maybe we'd have 150 here also like that, but we'd have zeros. That's the naive part. We're going to just say, you know what? Let's forget trying to estimate the covariance. Let's just treat these x variables as independent of each other. I know that's not right, but you know what? What are you going to do? I'm going to pretend it's they're independent, and you know what? It's going to be fine, right? You're like, no, they're actually dependent, and there's covariance. Yeah. You know, it's not that big of a deal, okay? And it turns out, you know, you make this naive assumption, and in most cases, you get away with it, okay? If the means of each class are kind of different enough, then the naive Bayes classifier works great, all right? And then if the means were all close to each other, like the true model, like the naive Bayes classifier doesn't do great, but the true model does terrible too. So it's like, you know, you don't lose a whole lot by doing this, and your life becomes a lot easier by doing it this way, okay? So, so basically, you might have, let's say our x variable, or x vector is like x1, x2, and x3. So the true would be our x vector comes from a multivariate Gaussian, multivariate normal with vector, you know, x1 bar and x2 bar and x3 bar, and then you have to have some covariance matrix which is, you know, 3 by 3, right? And this thing could be hard to estimate because you've got to do one of these for every single class that you have, right? So this needs to be estimated for each class. And who knows? Maybe that's not so easy, okay? All right, naive Bayes. Now you just do a bunch of multiplication, all right? We're going to just say our x vector is going to come from normal, where the mean is x1 bar and standard deviation 1, okay? Multiplied by normal, where the mean comes from x2 bar and standard deviation 2, right? I guess I should use S rather than sigma. And so it's just the product of 3 univariate Gaussians. And this is like way easier, right? So this is going to be your, how to calculate your likelihoods. And then, and everything else is the same. You multiply it by a prior probability, and then you do this for all the classes. You add them all up to get your marginal, so that when you find the posterior probability of each class, it's they add up to 1. Is that okay? So naive Bayes, we're going to just treat our joint distribution across all x's as just the product of several independent Gaussians, or whatever distribution you have, right? Maybe it's not here. I just assumed all 3 were Gaussians, but you know, one of them could be exponential or something like that. Okay, and then you know, and that's really hard over here, right? Like, is there a joint multivariate normal / exponential? There's probably something, but I have no idea how to estimate that. So we just keep our life easy using using these things. All right, is that okay? Yes? Yeah. There is a naive Bayes function in R, and I forgot how to use it. I'll look it up, okay? All right, I'll look it up. Your homework is to write your own naive Bayes function, okay? And you're gonna do our favorite iris data set. All right, and we got 10 minutes left. That's okay. I'm gonna cover K-nearest neighbors because that's also a very easy classification algorithm, okay? All right, so K-nearest neighbors. I'll just start off with a 2D example, but it's very, I should write, okay, here we're talking about K-nearest neighbors, also called KNN. All right, so let's say we've got stuff like this. Okay, and then, so I've got I've got the red team and the blue team here. And let's say I have an observation right here. Okay, and you have to guess, what is this thing going to be? Okay, so this is how K-nearest neighbors works, right? So you have your training data, and you have your new observation, x new. Okay, so this would be our x1 and our x2, right? And what you do is you measure the distance from your new data point, x new, to every other data point in the data set. Okay, distance, how do we measure distance? It's going to be what is this? XA minus, I don't know how to do it with X. I'm going to change this to Y. We'll call this X and Y, just to make my life easier, all right? So we'll call this X and Y. All right, so we have X1 minus X2 squared plus Y1 minus Y2 squared, it doesn't matter. And then you take the square root of that, right? So this is just Euclidean distance. There's other distance metrics. Such as Manhattan distance, which is if you don't know how to walk in diagonal lines, you have to, and you can only like walk parallel to the axes, then it just becomes the absolute value of x1 minus x2 plus the absolute value of y1 minus y2. Right? So it's they call it Manhattan distance because it's like if you had to get to, it's like how many blocks do you have to walk in Manhattan? Because you can't walk through diagonally through a skyscraper. So, okay, Euclidean distance, this would be as the crow flies, and this is like I'm driving on a grid. Okay, so anyway, you have different distance metrics. Euclidean's probably the most common one. right? And this is easily expandable for higher dimensions, okay? So you measure the distance from x new to every other data point in the data set, okay? And then you sort from least to greatest. Okay. And then you choose the k nearest neighbors. So k is some arbitrary number. K is an arbitrary value. Number like 5, okay? Usually we like odd numbers, okay? Especially if there's 2 classes, odd numbers are the best because you won't end up with a tie. And then each neighbor votes their class. Okay, so if we look at this one, we'd say, all right, let's do our 5. Oh, this is going to be kind of hard, but okay. All right, I'm going to just do our 3 nearest neighbors, which will be these 3, right? So we say, okay, what are the 3 nearest neighbors I have? These ones have the shortest distances. And then we'd say, okay, what are the votes? We have 2 blue and 1 red. Therefore, our classification will be blue. And that's it. That's like really easy, right? So you just start off with your new data point that you're trying to figure out what is the classification for this. And you say, okay, you know what, let's figure out who my nearest neighbors are. So that requires you to go through the whole data set because there's no, like on a plot, it's easy for us to visualize which ones are the nearest data points. But you know, in a data set, when you got a giant table, it's not that easy. So you just figure out the distance to every single other point. Then you sort it from least to greatest. And then you say, okay, I want my k nearest ones. And then each one votes their thing. Okay. Sometimes you end up with ties. Like, for example, if we had k is equal to 5 and I have 3 classes, it's possible to get like 2 red, 2 blue, and 1 yellow, or something like that. Okay, that's possible. And then you have to decide, all right, between the 2 red and the 2 blue, I've got to pick, right? So then you have a few options. You can say, okay, well, what if I reduced it down to the 3 nearest neighbors or the 1 nearest neighbor? So oftentimes, if you have a tie, you will say, okay, between those 2, which one has the nearest, the one that's closest to me? And that one will usually be like the tiebreaker. But it's very easy. K-nearest neighbors is a very easy classification algorithm. And this is kind of just the basic idea. The interesting part is, you know, what is the K that you should choose? And this brings in the whole bias variance trade-off question, okay? If you use a small k, you are more prone to overfitting your data if you use a small k. Okay? And if you use a too big of a k, then you're prone to underfitting your data. And so I guess we can explore this a little bit next week. But basically, this I've posted homework for, and it is in my opinion, it's straightforward, but you've got to think through it in your coding. You're going to code up by hand a k-nearest neighbors algorithm and a naive Bayes classification algorithm. Okay, these are 2, I think, straightforward classification systems, but you do have to think a little bit about how to write your code. So so we'll leave you guys with that, and we'll see you guys next week.